Alright, welcome back to our third lesson on trigonometry. We're going to expand our horizons today and start to talk about the sine and cosine ratios as well, and how we can use those to find angles. So, for tangent, right, it was the ratio between two specific sides given a reference angle, right? It compared how long is the opposite side compared to the adjacent side for a specific angle measurement. Right? But what if we don't have the opposite or the adjacent? Let's say we know the hypotenuse. Right? Unfortunately, tangent is not going to be our friend in that case because it doesn't compare the hypotenuse to any of the sides. Right? The ratio is strictly how the opposite and adjacent compare. But we do have two other ratios. The sine ratio is going to compare the opposite side, right, to your reference angle. If we're still talking about, say we're all talking about angle A, the sine ratio tells us how the opposite side compares to the hypotenuse. And if you already guessed it, the cosine angle ratio compares the adjacent side to the hypotenuse. So out of three sides, three ratios, we can compare all three to each, right? Opposite to adjacent, or opposite to hypotenuse, or adjacent to hypotenuse. We have a little acronym for these. This acronym will follow you for the rest of your life. You're welcome. And we call it SOHCAHTOA. And what this means is it is a friendly reminder, a helpful acronym that reminds us that sine, right, the sine ratio, talks about the opposite and the hypotenuse. All right, the O and the H tell us the sides. The S tells us which ratio we're talking about. So we have SO, and then we have CA, the C telling us that this is the cosine ratio, with A representing adjacent and H representing hypotenuse. And then the TOA telling us the one that we focused on for the most part already. This is the tangent ratio that refers to the opposite and then the adjacent. And it tells us them in order of numerator and then denominator. So, right, so sine and then opposite hypotenuse tells us that opposite goes on top, like we see up here, and hypotenuse goes on the bottom. Cosine, that AH, right, tells us adjacent goes on top, hypotenuse goes on the bottom. So I'm going to use that a lot, SOHCAHTOA. You'll continue to use it. You'll probably remember SOHCAHTOA. If you don't remember anything else, you'll remember SOHCAHTOA when you're in your 30s and reminiscing back to the good old days of Math 10C. So we're going to do the exact same thing that we did with tangent when using sine and cosine. We just have different ratios set up, right? So there's different side lengths that we're comparing. So to find the angles, so we have to use that inverse to unsine or uncosine or untangent, right? That angle to isolate. And if we find side lengths, that's where we're going to cross multiply, right? Isolate, and we use the regular function, right? We take the sine of the angle. The only time we use the inverse is when we're trying to find that angle. Some other terms we use a lot when talking about trigonometry and talking about angles in general is the angles of inclination, or specifically the angle of elevation. And these are angles that are measured up from the horizontal. So a lot of the time talking about line of sight, right? If you're standing here, and here's your line of sight, right? And the angle of inclination, so you turn your head up, right, from the horizontal up, that's going to tell us the angle of inclination or the angle of elevation, right? We use it a lot for talking about how steep a hill is, right? How tall a mountain is, angle of elevation. So from bottom to top. Occasionally you might hear the term angle of depression, right? And that's angle from the horizontal down. We won't look at that much here. So, given the ratio, find the measure of angle A to the nearest tenth of a degree. All right, so we use the term ratio as usually to mean a fraction, but it can also just be a decimal value. All right, so sine of angle A here says it's 0.682. All that tells us, right, if I'm thinking of the SO part of SOHCAHTOA, is that the opposite length times is 0.68 times the hypotenuse, right? The opposite length is smaller than the hypotenuse, which is always going to be true, right? At a ratio of 0.6872, technically to every 1 unit on the hypotenuse. So this is a ratio. It looks a little funny, but it's still talking about the comparison because we're using sine of how the opposite and the hypotenuse sides compare, right, in terms of length. Which one is larger by what factor? Like we've done in the past, if I'm trying to find an angle, right, I want to isolate A, but right now it's stuck inside this sine function. So I'm going to inverse sine, right, just like we did with the tangent. I'm going to inverse sine the other side. If I could spell sine, that would be helpful. Alright, so it's going to give us something that looks like angle A. We pulled it out of that sine. We got rid of the thing holding it in, right, by doing the opposite operation. I'm taking the inverse sine of 6872. Right, because what I do to one side, I have to do to the other. And there's no sine to cancel out on this side. So when I pull out my calculator, right, you're either hitting the second button, if that's what your calculator looks like, or you're finding this sine minus 1. Right? An inverse tangent is not going to help us deal with a sine function. An inverse cosine is not going to help us deal with a tangent. We want to match. And our decimal value was let me look at it again, 6872. Oops. 872. And as you can see there, it's telling us 43.4, right? And that's the angle. That was angle A, 43, and it says to the nearest tenth, round that to 0.4 degrees. Okay, so what that's telling us is for any angle that's 43.4 degrees, this is how our opposite and hypotenuse sides relate. Right? If I was to take the cosine or the tangent of the same angle, it's going to give us a different ratio because it's still talking about the same angle, it's talking about the same triangle, but it's comparing two different sides. Looking at the second one, B, the cosine of angle A is 3/8. So again, thinking back to our SOHCAHTOA, the ka part in the middle tells us about cosine. I'll add the toa on the end just for the sake of finishing it off. Right, but here we're talking about angle A, same angle, or a different angle in this case, but how does an angle compare the adjacent sides to the hypotenuse sides in this 3/8 ratio? Right? If we had an adjacent side length of 3 and a hypotenuse length of 8, what angle would we have that's creating that? Right? The angle that's adjacent to the side length of 3 and has a hypotenuse of 8. So, same idea. I need to uncosine that left side, right? Because I have to undo the fact that A is trapped inside that cosine. I then have the inverse cosine of 3/8. Plug that into my calculator. Again, going to my inverse cosine of 3/8. And it gives me an angle of 67.97. Round that up gives us a 68.0 in this case. Whoops, 68.0 degrees. Right, so only a 68-degree angle would cause this ratio between the adjacent and the hypotenuse. If we make the angle a little bit bigger, right, then the adjacent side length might get a little bit longer. If we make the angle a little smaller, then the adjacent side length might be a little shorter in comparison to the hypotenuse, right? It's just a comparison of those two sides. For any similar triangle, any triangle with this 68-degree angle. So let's solve for angle S to the nearest degree. Let's find some angles here. Looking at this first one, same thing is going to hold true, right? Let's call it theta. I'm always going to start by labeling my triangle. It's going to be extra important now, right? Because I want to figure out what side is my opposite side Well, it looks like this side length of 23 is opposite. This side length of 35 is going to be my hypotenuse, right? It's across from that right angle. And this unknown side is my adjacent. So here's where we have to use a little bit of critical thinking, a little bit of problem-solving skills. All of these ratios only have space for three things, right? Two side lengths and an angle. If I'm trying to find an angle, I really only care about using two side lengths. So here, I'm trying to find this angle, right? I need to know that. That has to be my unknown. So that means I have to know everything else in my ratio. I have to know both sides for my ratio. Well, the two sides that I do know are the opposite and the hypotenuse. So this is where that acronym is going to come in handy. I'm thinking SOHCAHTOA. Right, which of the ratios am I going to use that involves the two pieces of information that I have, right? Because I want to use the information given. I need to find something that involves the opposite side. So already cosine is not going to work for us. We'd have too many unknowns. I don't know the adjacent side, and I don't know the angle. And tangent is also not going to work because I still don't know that adjacent side. So I want to use the sine ratio here because that's going to allow me to fill in two of my three unknowns and solve for that angle. So let's start by writing out the formula. Sine theta is opposite over hypotenuse. All right, always start by writing your formula just so I know it's clear to everyone what your goal is, what you're trying to do. Then I will plug in those values, right? I had two side lengths. My opposite length was 23. My hypotenuse length was 35. Make sure that your hypotenuse is always longer than the other side, right? Otherwise you've mislabeled. And I leave my theta blank, right? That's my unknown. That's what I'm trying to solve for. Because I'm solving for an angle, I do the inverse of my trig function. And because I was using sine, I'm doing the inverse sine. Let me rewrite that. Inverse of sine of that ratio. 23 over 35, right? And I'm doing that because I had to inverse sine the left side. That's why the sine is gone from the left side now. This is where the calculator comes in. I take the inverse sine of 23 divided by 35, right? If you want to find that ratio as a decimal first, if that helps, you're welcome to do that. 41.08. So let's call that 41.1. Oh, to the nearest degree, sorry, 41. So the angle that creates that relationship between the opposite and the hypotenuse is 41 degrees. Let's look at B. So same idea, I want to find angle S. Let's start by labeling that one. Now I've decided that's the angle that I'm referencing. I can label the opposite, the adjacent, and the hypotenuse in relation to this theta, right? The opposite side, opposite of S. Even though the 12-foot length is opposite angle R, that's not the angle I'm referencing. Now we're going to use that same idea as before, right? I have SOHCAHTOA. I'm looking at what I have and what I need. Right? I need theta. Well, they all involve an angle, so that doesn't help. But I have the adjacent and the hypotenuse. So that's going to tell me that I want to use cosine as my ratio because that involves the pieces that I have. Right? Sine and tangent would have too many unknowns for us to solve. So cosine theta is the adjacent on top, hypotenuse on the bottom, right? We go in order, numerator, denominator. My angle is still unknown, so I'll leave that blank, but I'll fill in my adjacent length and my hypotenuse length. Again, trying to solve for an angle, so that's where that inverse function shows up. When I solve for a side length, we won't see this inverse function. 12/18. Right? If we wanted to reduce this fraction, we could. That would just tell us basically the ratio for a similar triangle. but I'm doing the inverse cosine of 12 over 18. And I get 48.1, 48.2, so rounding to the nearest degree is going to be 48 degrees. All right, so a 48-degree angle creates that ratio between the 12 and the 18-foot lengths. Let's look at some more application problems. A water bomber is flying at an altitude of 5,000 feet. The plane's radar shows that it is 8,000 feet from the fire site. What is the angle of elevation of the plane from the fire site to the nearest degree? All right, so first thing, it's telling us the water bomber is flying at an altitude of 5,000 feet. So that tells us the vertical distance to the ground, right, is 5,000. We don't measure that one at an angle, right? Altitude is a straight vertical distance. So, right, we have a horizontal line to connect that. This is the ground level, right, from the bottom of the fire. And then it's also telling us that the plane's radar shows that it is 8,000 feet from the fire site. We can assume that's direct, right? The plane is trying to reach the fire. That's going to tell us here that our hypotenuse is that 8,000 feet, right? Because the plane, from the plane to the fire, is that distance we're talking about, not the distance along the ground, because the plane isn't traveling along the ground. And again, our right angle is always made by any vertical and horizontal distance, right? That 90-degree angle. What is the angle of elevation? So remember, that means from the ground up, right? Of the plane from the fire site. Right, so the angle of elevation from the fire site, angle up to where we see the plane. Right? This is the angle we're looking for. This is our theta. This is our unknown. So, same as before, we have a right angle triangle. The only difference is we have some really great clip art of flames in a plane. We're still going to label our sides opposite. All the way over here, this 5,000 feet is our opposite. This 8,000 feet is our hypotenuse, right, because it's across from that right angle. So that tells us our adjacent is along the bottom. We think about what we have and what we want. We want this angle, and we have the opposite and the hypotenuse. So thinking back to our acronym, SOHCAHTOA, the one involving the things we know, right, the one involving the opposite and the hypotenuse, means we're going to be using a sine ratio to solve this problem. The sine ratio has enough information to solve this. The other two do not. So sine theta is opposite over hypotenuse. Plug in our values. We don't know the angle, but we know that the opposite length, right, the altitude of the plane is 5,000 feet. We know that the hypotenuse, the distance from the plane to the fire, is 8,000 feet. I'm going to take, right, like we've done before, I take the inverse of my function. That's what gets the angle out, right? It's currently stuck inside until we unsign it, right? But I have to do the same thing to the other side. So I'm taking the inverse sine of that whole right side, that whole ratio, 5,000 over 8,000. Pull out my calculator. Inverse sine of 5,000 over 8,000. And I get 38.68, right? 38.7. To the nearest degree, we're going to round that to 39 degrees. So we can say the angle of elevation from the fire to the plane is 39 degrees, right? And that's information that can be used. It can be sent to the pilot to figure out how much he needs to decrease his angle to reach the fire, right? It can be used for a variety of purposes, and actually trigonometry like this is done a lot in real life. So we're going to finish off this lesson here today with that question. Right? Notice that it's really not a whole lot different from using that tangent ratio. We just have the one extra step of deciding, all right, am I going to use sine, am I going to use cosine, or am I going to use tangent? Really important that we label our sides and we clearly identify what information do I have and what information am I trying to find, and pick the ratio that I can fill in 2 of those 3 blanks. So when we come back with our 4th lesson, we're going to look at finding some side lengths. So here we found only angles. We're going to use all 3 of those ratios again, specifically sine and cosine, to find some unknown side lengths when we're given the angle. So I'll see you in that next video. Please send me an email if you have any questions. Be sure to hit that subscribe button below.